Welcome to the Explainer. We spend all this time building these incredible models, but how do we really know if they're going to work out in the wild? Today, we're diving into the techniques that help us build models we can actually trust.
So let's tackle one of the biggest headaches in data analysis, certainty. You've built a model, it looks fantastic on paper, but is it going to fall flat on its face when it sees new data? Let's imagine an analyst wrestling with this very problem. So the analyst looks at their results and says, all right, check this out. My model's got a super low error rate on all the data I used to train it. I mean, that's got to be good enough, right? But our guide wisely pushes back. Well, not so fast. What you're looking at there is the in-sample error, and honestly, it's usually way too optimistic. Think of it like grading your own test when you already have the answer key. The real exam, the thing that actually matters, is the prediction error on data the model has never ever seen before.
And this all comes down to something we call the bias variance dilemma. See, if your model is super flexible, it can get so complex that it doesn't just learn the real pattern in your data, the signal. It also starts learning every little random quirk and bit of noise. So yeah, it'll look like a genius on the training data, but that's because it's basically just memorized the noise. It'll completely fail on new stuff.
Okay, our analyst gets it. That's a huge trap. So they ask, okay, how do we get a more honest look at how our model's actually going to perform, without just having to wait around for brand new data to show up?
Great question. And that brings us to one of the most powerful tools in our arsenal, cross-validation. The best way to think about it is like giving your model a whole series of mini final exams. You take one single piece of data out, train the model on everything else, and then test it on that one piece you held back. Then you do it again and again for every single data point. When you average out all those little test scores, you get a much more realistic grade for your model.
And look at this. This chart just lays it all out perfectly. You've got this complex cubic model, and on paper it looks amazing. In-sample error of just 16.66. But the moment we run cross-validation, its real-world error jumps all the way up to 20.66. That huge jump? That's the classic red flag. We just caught overfitting in the act.
The analyst is sold on validation, but now they're curious. Wow, okay, that makes total sense for testing a model's performance. But what about stability? Can we use these kinds of resampling ideas to figure out how much our estimates might bounce around? Like, if I had a slightly different set of data, how much would my results change?
Absolutely. And for that exact problem, we have another brilliant technique called bootstrapping. It's this really clever way to basically simulate what would happen if you had a bunch of different data sets, but you do it all with the one you've already got. The trick is you treat your sample as if it were the whole population. So here's the magic behind it. You just keep taking new samples from your original data, but, and this is the key part, with replacement. That just means you can pick the same data point more than once in a single sample. For each of these new bootstrap samples, you calculate whatever it is you're interested in, like a model coefficient. You do this thousands of times, and what you end up with is a whole distribution of that statistic. It shows you the range of possibilities, all without collecting a single new piece of data. It's pretty amazing.
This gets the analyst thinking. Okay, so this is getting really interesting. We can validate models, we can check their stability, but can we actually use these resampling ideas to, make the model better, to actually improve its predictions?
You bet we can. And that leads us to a technique called bagging. The name sounds a little funny, but it's short for bootstrap aggregating. And yeah, you guessed it, it literally combines the two big ideas we've just talked about.
So here's what bagging is so good at. It is first and foremost a variance reduction technique. It's designed to take down that instability we talked about. By creating a bunch of models on different bootstrap samples and then just averaging their predictions, you smooth everything out. Take a look at the chart. The bias doesn't really change, but look at that variance. It just plummets. This is how you tame powerful but sometimes wild models and make them way more reliable.
And it doesn't even stop there. People have built on this idea with even more advanced methods, like arcing. That's short for adaptive resampling and combining. It's kind of like bagging, but it's smarter. It builds models one after another, and with each new model, it deliberately pays more attention to the data points that the previous models got wrong. It basically forces the system to focus on the toughest problems.
Our analyst is impressed. This whole toolkit is just incredibly powerful. But it does make me wonder, with all these different methods, is there just one best one? A silver bullet we should always use.
And that's really the million-dollar question. The answer gets right to the core of what data analysis is all about. And no, there is no single best tool. The key thing to remember is that intelligent data analysis isn't like following a cookbook. It's not about just applying a directory of tools. It's a journey of critical assessment, exploration, testing, and evaluation.
Right. It's all about thinking critically and matching the right technique to the right problem. Our goal isn't just to blindly run some code. It's to use these powerful techniques thoughtfully, to really peel back the layers and uncover the true story that's hidden in our data.
So when you think about it, these resampling methods aren't just clever statistical tricks. They're like a powerful set of lenses. They let us see the real story in our data, validate what we think we found, and, most importantly, build models that we can actually trust when it really matters.
Hey, if you found this explainer helpful, we'd really appreciate it if you'd like, share, and subscribe for more. Thanks for tuning in.